Hello, good morning everyone. My name is Vinicius Giggs, and today I'll talk a little bit about how to integrate behavior cloning and reinforcement learning for improved performance in dense and sparse reward environments. And this work is a collaboration between Texas A&M University and the U.S. Army Research Lab. So first, to start this talk, I'll just give you a quick background on the cycle of learning, which is one of our previous work. So in the cycle of learning, we wanted to combine kind of human interaction modalities to reinforcement learning. So basically, how can we combine learning from human demonstrations, learning from interventions, evaluations, to reinforcement learning? But there was always a challenge when we try to combine learning from human demonstrations to reinforcement learning, because the loss functions are just totally different. Just training a model with imitation learning loss and just switching directly to reinforcement learning on the same model, there was always kind of dropping performance, and that's what this paper is trying to address. So how can we still leverage this human demonstration and go to RL, but kind of without kind of loss in performance? So there are three key ideas of this paper. So the first one is this key idea of doing a pre-training phase with previous test demonstration data. So in this approach, we're using an actor-critic architecture. So we do as a pre-training phase with previous collected data, kind of to initialize both actor and critic networks without interacting with the environment. The second idea is a combined loss function. So since doing the switch of loss functions between imitation learning loss to reinforcement learning didn't work well, we are proposing this combined loss that combines both behavior cloning and the reinforcement learning loss together to learn directly with just one loss throughout the whole training process. And the third key idea of this paper is this component analysis. So since we're kind of proposing different things, we're proposing in pre-training phase a combined loss functions. So we want to see what is the impact of each one of these kind of components in the total performance of the agent. A little bit about our approach. So we start by collecting expert demonstrations of the test to be learned. So you see here on the left, we're using the lunar lander continuous environment, which is the lunar lander but with continuous actions. And we have lunar lander for two different loss functions. So first we have it for the dense reward case, which is the standard loss function for lunar lander. So basically at every time step, you give a reward based on kind of how well you are driving your lander towards the landing pad. And the sparse reward case is something that we implemented specifically for this paper, which kind of basically used the same loss function, but instead of giving a reward to the agent at every time step, we kind of just hold this reward and just sum them all together and just give at the end, at the final time step, we just give to the agent. So it is a sparse reward setting. And the task on the right is another custom task that we implemented in Microsoft AirSim. So on that, we're trying to land the squad rotor on that landing pad, and then the agent has access to visual features from bottom facing camera, IMU data, so kind of inertial data from this vehicle, and controlled by 4 continuous actions that control roll, pitch, yaw, throttle. So after we collect all this expert data, we put all those trajectories and transitions on an expert buffer. So you see here that we have 2 separate buffers, an expert and an agent buffer. After we collected all the expert data and put on the expert buffer, we go to the pre-training phase. So on the pre-training phase, we sample all the data we have from the expert buffer and train both actor and critic networks using this combined loss, which you see here on the right. So there are 3 main components of this combined loss. The first one is the one-step return Q loss. So that's how you train your critic. So basically, that's you train by temporal difference error. that's the same for the Q learning. And the second component is the actor Q loss, which is the gradient of the Q function that you're learning with your critic. So that's pretty standard on actor critic architectures, and also DDPG, for example, deep deterministic policy gradient. And the third component is the behavior cloning loss. So in our case, since we're dealing with continuous actions, our behavior cloning loss is a mean squared error. And then you have those three lambdas, so lambda BC, lambda A, and lambda Q1, which you can basically control how much you want of each component in this combined loss function. So this was the pre-training phase, all done offline with only data that we collect from the expert. So now during the training phase, the agent interacts with the environment and just on a standard way. And now all these new trajectories that are being collected are stored in the agent buffer. And then now actor and critic networks are trained, but we combine data from both buffers. So there are different ways you can combine data from two buffers. So what we do is we use the fixed ratio, which is the same thing that they did on this paper. You can see on the bottom, observe and look further. So they got pretty good results on Montezuma Revenge, which is a challenging Atari task with a sparse reward function. So they use the fixed ratio, which is the same thing that we do. So we sample 25% of our batch size from the expert buffer and 75% from the agent buffer, and then we sample all this data, then compute the loss using this combined loss function and train the actor and critic networks. So here are some qualitative results. So we can see that our approach corrects for inefficiency in human demonstrations. So on the left you see human demonstrations for the task. They're not perfect, but that's what we have to start. And at the end, the cycle of learning is able to leverage this imperfect data and learn, correct all those inefficiencies and learn a better policy. Not only that, you see on this new task, this approach is also able to generalize to variations in the environment. So on the left, if we train this policy using the cycle of learning with wind, it is able to generalize to, for example, a condition where you have no wind or with small variations in wind velocity. The same policy is able to generalize. The baseline for this work, so it's just standard behavior cloning. So let's say we collect all the expert data, and what if we do just behavior cloning? How well this is going to perform? The second baseline is deep deterministic policy gradient, which is a standard deep reinforcement learning algorithm. So if we have no expert demonstrations at all and just do RL, what is our performance? The third baseline is the closest one to our work, which is the demonstration augmented policy gradient, the APG, which also leverage data collected by expert, but it does that on a policy gradient fashion. And you see all the reference for those papers at the bottom. On the left here, you see the results for lunar lander continuous for the dense reward case. And you see the dark blue is the cycle of learning. The red one is the just RL using the DDPG. The light blue is the DAPG, which is also a combined approach. And the dashed black line is a behavior cloning. So you can see that when you do the pre-training phase and you have this combined loss, you start with the higher performance, and the training is just stable and converges to a stable result, which is higher compared to the other baselines. Same thing happens for the sparse reward case, where RL has just a harder time trying to learn, but both the APG and cycle of learning, they are able to learn the task, but the cycle of learning has just a higher performance. And the third one is for the landing in Microsoft AirSim, another sparse reward task. And you see that the cycle of learning and the APG actually converge. They converge to the same result, although the cycle of learning starts with a higher performance. So just shows how this pre-training phase it is affecting the policy. But now, just a more kind of rigorous component analysis of each kind of component of this approach. So first, we wanted to kind of evaluate specifically that. What are the effects of my pre-training phase? So what we do is we compare the cycle of learning, the standard one, compared to the cycle of learning without the pre-training phase, which is without the pre-training phase is this purple line, and the cycle of learning is the blue line. So we can see that just using the combined loss, collecting the data the same way, using the same data, but if you don't do the pre-training phase, your policy will start with a way lower performance compared to if you actually do the pre-training phase. And that might not be that important depending on the task that you have, but if you're dealing with real-world robots, you want to start your kind of online training, you want to start with a higher performance so you have fewer catastrophic actions. So you don't want to start with a bad policy. So that's what we provide with the pre-training phase, everything being done offline. So the second component analysis is the effects of the combined loss. So we want to see how much the behavior cloning component is contributing to the final results. So you can see here on the right, we have behavior cloning, the black line, and we have that first condition I talked about on the beginning of the talk, which is behavior cloning, standard behavior cloning, and then you switch to just standard RL with the same model. The purple line is the cycle of learning without the behavior cloning component. And the third one, the blue line, is the cycle of learning. So you can see that kind of this behavior cloning loss helps grounding the policy to a good performance. The final component analysis here measures the effects of human experience replay sampling. So here basically we evaluate the difference between sampling from the buffers with a fixed ratio compared to prioritized experience replay, where you have a single buffer and then you sample those experts or agents. It doesn't really matter. The only thing that matters is the temporal difference error. So that's how the samples are ranked. So for this case, we have two scenarios: scenario where you have a sparse reward and another scenario where you have a dense reward. And as you can see here on this plot on your right, they mostly perform very similarly, with exception to the purple curve, which is the cycle of learning with the prioritized experience replay in the sparse reward case. And this happens because after some time training, you start based on the temporal difference error, you might start kind of losing those expert samples and not sampling that anymore, since the temporal difference error is smaller. But even though it is smaller, it helps grounding the performance, which is what you see on the other approaches with the fixed buffer ratio. So in summary, this work enables this transition from behavior cloning to reinforcement learning without performance degradation. Plus, it improves the reinforcement learning overall performance and training time for both dense and sparse reward scenarios. And if you have any extra questions, feel free to reach out to any of the authors. You have all the emails here on the left. And also feel free to come to our project page, where we have videos and plots and hyperparameters and everything you want to know about this paper. Thank you very much.